All right, I'm going to go through investigation 1.2. I've done a couple of things on here, but not much because I figured it's best to kind of work through this. So basically what's happening here is you get some models of rectangles with set perimeters. So if you remember a fixed perimeter, I put it on the bottom of your page as well, basically means that all of the rectangles have the same perimeter. So they're basically saying like, create all the rectangles you can that have like a perimeter of 32 or a perimeter of 36 or a perimeter of 24 or whatever the set perimeter is. It's your job to try to figure out what that actually is. So you have in letter A, you have length, a correlation between length and area. You can see that as the length increases, we kind of get to a tippy top point here. So our lengths go from 0 to 20. And then our area kind of maxes out. There's a maximum point there. And then as we go from 20 on to like 40, that we have a area that's kind of increasing, and then it gets to a tippy top point, and then the area decreases. So if you're describing the shape, you should have used the word parabola, right? So we've got a parabola that looks kind of like the St. Louis Arch. So you should have an idea just based on what we've done so far of how this relates to the parent graph a little bit. And you might even be able to come up with an equation for it, but we're not actually focusing on that right now. We're just focusing on kind of how rectangles relate to quadratic relationships. So what is the greatest area possible for a rectangle with this perimeter? So we still don't really know what the perimeter is yet. We're going to get to that a little bit later. And then what are the dimensions? So if we look at this, the highest area that this rectangle or that these rectangles might have lies at the very, very tippy top point. So this would be the greatest area. And that would be 400 square meters. If I follow this down, right, so this would be my maximum point. I know that the dimensions of this rectangle, I only have one length here, right? If I look at any other of these amounts, we can see, because we have symmetry happening, if I was at a length of 15, I'd be at about 375, about 375 square meters, and 15 would then kind of line up with 25. So a length of 15 and a length of 25. That would mean that my rectangle, and again, I'm not to scale, but my rectangle would be 15 by 25. The one in the middle, though, I don't have any other dimension besides 20. So in this case, my dimensions for this rectangle must look like a square. So the very tippy top point, and you learned this in sixth grade when you guys worked in covering and surrounding. I believe they went through an investigation or two that dealt with fixed area and fixed perimeter. I could be wrong. I'm not sure if the books have changed too much, but they're, when you make rectangles, basically what you find when you have fixed perimeter, if you have a set amount of rectangles with fixed perimeter, as the rectangle gets closer and closer to looking like a square, whatever rectangle you can get to look most like a square, that will always give you your greatest possible area. So in this case, we've got a 20 by 20. So what is the area of a rectangle whose length is 10 meters? If I go up 10 and then I put a little dot there, I know that it is 300. So I know that this area is 300 square meters, not 330, 300. And then it goes on, what is the area of the rectangle whose length is 30? Well, if I go up to 30, I notice that I've got kind of a correlation here, right? So 30 meters is also 300 meters squared. So what does that tell me about this rectangle? Well, we're dealing with the exact same rectangle. So if I'm at 10 meters for a rectangle, then I should have a 10 by 30 rectangle. So 10 times 30 will give me that 300. So these two lengths are part of the same rectangle. And that's the relationship. So any of these that are kind of symmetrical with one another, that are in the exact same position, only on the other side of the parabola, that will give you the length and basically the width of that rectangle. What are the dimensions of the rectangle with an area of 175 square meters? Well, if I go to 175, I'm looking at 5 meters in length. And then I can also go over and see that here we have 35. So these two line up together. So my dimensions are 5 by 35. What is the fixed perimeter of the rectangle represented by the graph? Explain how you found the perimeter. Well, if I know that all of these points line up and these points that are symmetrical with one another create the rectangle, I can take any one of these rectangles and then figure out what the perimeter is. So I can do 10, 10, 30, 30, 15, 25, 25, 15. I can also take my 20, right? So my rectangle that's 20 by 20, I've got 20, 20, 20, 20. So all of those should add up to be 80 meters. So 80 meters for that. 30, 30 is 60, plus 10 is 80. When we come down to the data table, I wrote some things here for the bottom ones. What patterns do you observe in the table? Compare these patterns with your what you observed in the graph in question A. So what we see here is basically, if we looked at the graph, we noticed that we were increasing our area. So as the length increased, our area increased up until a certain point, and then it kind of gets this kind of tippy top shape here. We also know that the increase gets lower and lower, so it's still increasing, but it's increasing at a lower rate each time. We get to the tippy top, and then it decreases at that same rate. So it decreases, and that decrease will increase as well as you go down. You see that in the data table by looking at kind of the rate of change here. We know it's not linear because we're not going up at a constant rate, but we see that we have a change in 11, a change in 9, a change in 7, 5, 3, 1. When we get to this 6 and 36, this is the point where things start to change, right? So this should be my tippy top point. If I plotted these points, I would see that I would be going up in the same way up until my area is 36, and then that would be my tippy top point, and it would start to go down again. So now I've got a decrease of 1, a decrease of 3, 5, 7, 9, and 11. Something very particular to quadratic relationships is this pattern that you see. This we would call the first difference. So if you look at this kind of section right here, how the change happens, plus 11, plus 9, plus 7, the second difference will have should be the same number. So in any quadratic relationship, as long as you're going up by a constant value in the x part of it, or the x component, the y component, the second difference, will always look somewhat linear, but it's not linear. It'll just kind of look, it'll be the same difference. So here I have a difference of 2, go down by 2, go down by 2, go down by 2, down by 2, down by 2, down by 2, and so on. So that second difference will have the same number that happens there. That's extremely important to know if you're ever given data tables and it asks you, which of these data tables is a quadratic relationship. The second difference will always show that. The fixed perimeter for the rectangle represented by this table, well, when I look at these, the same way as the graph, I'm looking for the symmetry, right? So I've got 11 and 11. I've got 20 and 20, 27, 27. I can pick any of these. I can pick any two. I can also pick the one in the middle that doesn't have a partner. So we know that this one is a square. So this should be the square, right? So since I have a square here, I'm dealing with a 6 by 6. So 6 and 6 and 6 and 6. So I would have 24 meters is what I would have there. I can do that with the 10 and the 2. So here I can do these with any of these. So this would be a 10 by 2. So 10 plus 10 plus 2 plus 2 gives me that 24 meters. I can pick any of the ones that match up together or that square in the middle, and then I can add up the side lengths for those dimensions. The greatest area possible for a rectangle with this perimeter and the dimensions, we talked about that. So our tippy top point, the greatest area is going to be 36 square meters for this. And then the dimensions, excuse me, the dimensions are going to be 6 by 6. 6 meters by 6 meters. All right, so now we come into the estimation. I've already highlighted these parts. Estimate the dimensions of a rectangle with this fixed perimeter and an area of 16 square meters. So basically what I'm doing is I'm looking at these two. So I notice that I don't have 16 square meters listed in my data table, but I do see that a rectangle with a length of 1 and then the other rectangle with a length of 2, I know that it should fall, my length should fall between 1 and 2 and also between 10 and 11 because this is where 16 would fall. So between an 11 and 20 square meters, I have a 9 square meter difference. So what I'm looking at here is to get from 11 to 16, it's about 5 numbers away. So 11, 12, 13, 14, 15, 16. It's a little more than halfway. So 5 spaces from 11 to 20, 5 spaces will put me at 16. It's a little more than halfway. That means that between 1 and 2, I should be a little more than halfway from that amount. So if I was estimating, I would say maybe about, I would estimate, I don't know, maybe 1.5 or 1.6, maybe even 1.7, because I'm trying to get to that. It should be about 16 meters squared. So it should be right between the 1.5, 1.6 range. And then I would do the same thing down here. Between the 20 and 11, there's a 9 space difference. So same thing here. It's about 16 is about halfway. So I might go to I would do it the other way though, right? So 20 to 16 is 4 spaces away. So I would be a little less than halfway. So I might say 10.4 or 10.5. So about halfway, but a little less than that. That should get me about 16 meters squared. So if you were anywhere kind of in this kind of 1.6 and 10.4 around that range, you should be somewhat okay with that. That should give you about 16 square meters. It actually gives you a little bit more. So you're about in that range. Suppose a rectangle with the perimeter has an area of 35.5. I circled that off as well. This one's a little bit easier because it is directly in the middle. So the dimensions here would be, you're looking at between 35 and 36. You have one increase in length. So you should be between 35 and 36 is exactly 35.5. 36 and 35 exactly 35.5. So you should be exactly in the center of 5 and 6 and exactly in the center of 6 and 7. So here that would be 5.5 by 6.5. So these would be your dimensions here, because 35.5 falls directly in the center of these two and these two, which means that it would fall directly in the center of 5 and 6, and then directly in the center of 6 and 7. I hope this helps to clarify a little bit about this particular page. That is it for now. See you soon. Bye-bye.